All right, welcome to chemical kinetics. Chemical reactions take time to occur. Some reactions, like the rusting of iron or the changing of leaves, occur relatively slowly, requiring days, months, or years. Others, like the combustion reaction that generates thrust for a rocket, well, that occurs really quickly. And as chemists, we want to be concerned with the rate or the speed of a chemical reaction. And so in this chapter, you'll see videos on rates and speed of a reaction and just what the definition is. That's this video. And then you'll see one on a way to illustrate those reactions called coordinate diagrams. And then we'll look at factors that affect the rate or the speed of a reaction, like temperature, catalysis, physical state, and we'll end with a series of videos on how concentration affects the rate or the speed of a reaction. So first of all, what is rate or speed of a reaction? So rate or speed of a reaction is the change in a given time interval. So for example, we look at our car and we say there is a rate or a speed to that, and we measure it in miles per hour. Well, in chemical reactions, we look at it as how the concentration or the pressure or the amount of a substance changes per unit time. So for instance, molarity per second is a good example of that. Or if it's a gas, it could be pressure per second or per minute or per hour or per day, depending on how fast the reaction is. Now, you have to be careful of these units because they'll want to trick you. So watch out for that. Sometimes they'll write molarity per second as molarity times seconds to the -1. And then you also know that molarity is moles per liter, so they might write it like this, moles per liter times seconds to the -1. Or if they want to be really fancy, they'll take this liters and also put that to the -1. So it'll be moles times liters to the -1 times seconds to the -1. So be super careful with the units in this chapter because they always come back to haunt you. So here's an example of a reaction, just a make-believe reaction, where we'll look at how the reaction changes with respect to time. So in this reaction, A goes to B. At time 0, before the reaction starts, let's say that we have 10 molar solution of letter A, and we have none of letter B. After 10 seconds of reaction time, we're down to 4 molar for A, and then that 6 that's disappeared has now appeared over here for letter B. So in this 10-second time interval, we can calculate the rate of appearance of reactant B. And we can calculate this by looking at the change in the concentration of B over the change in time. And the change in the concentration is always the final value minus the initial value. So 6 minus 0, which would be 6, and 10 minus 0, which of course would be 10. So 6 divided by 10 is 0.6. And so we'd put the units of molarity per second, because this would be in molarity and this would be in seconds right here. So that would be our average rate of the appearance of the of the product, letter B. We could also find the rate of disappearance, the average rate of disappearance of reactant A. And we'd do the same thing, but this time we'd do concentration of A change divided by the concentration time, or divided by the change in time. And so this now would be 4 minus 10, final minus initial, which would give us a negative number, which makes sense because this is disappearing, right? And then 10 minus 0, so we'd end up with negative 0.6. The negative sign comes because we always do final minus initial, and so this means it's disappearing from this side, and this is positive because it's appearing over here. Okay? Note, it's always final minus initial, so when you're doing the calculation, and then also know that these are calculations for the average rate. When we get to the last set of videos for this chapter, we'll look at the instantaneous rate of change of that as well. So in our example, A goes to B. Notice how the rate of disappearance was equal to the rate of appearance. And that happens to be because for every 1 mole of A, there's 1 mole of B. But what happens if it's not a 1-to-1 ratio? Like, for example, let's say we have 2x goes to y. Oh, okay. Well, then what we'd have to do is we'd have to take x and we'd have to divide it by 1/2. And so the disappearance of x would be 1/2 of the appearance of y with respect to time. And so for any general reaction, and I picked a big one here, coefficient AA plus coefficient BB goes to coefficient CC plus coefficient DD, we can write the rate in general terms as the disappearance of 1 over the coefficient of the change in concentration of A over the change in concentration of time is equal to the 1 over the coefficient of B times the change in concentration of B over the change in concentration of time, over the change in time. And then this would equal the appearances over here. So we have C, 1 over C, and then change in concentration of C divided by change in time. And that would equal 1 over D gives you the change in concentration of D divided by change in time. So notice how these two are positive, these two are negative because these are disappearing and these are appearing. So during this video, I hope you learned, first of all, that rate of a reaction is equal to the speed of the reaction. And it's always measured in concentration per unit time. Concentration can be used in molarity, or you could have pressures in there as well. And then time could be in seconds, minutes, hours, days even, as long as it is a unit of time.